We're going to talk about rational functions today and how to graph them. I want to start out though with just the shapes of graphs of power functions. Here I have an X and a Y axis. I'm going to confine myself to the first quadrant. And I'm going to do a P equals 3 power function. That's like the X cubed function, but it could be 50x cubed. It could be 0.003x cubed. We don't have a scale here. We're just going to draw the shape. I'm going to draw a horizontal line up here towards the top of the y-axis and a vertical line out here to the right on the x-axis. This is approximately a square, but it could be any rectangle. And I'm going to put a point right here. And now I'm going to come back halfway to the y-axis. And I'm going to draw another vertical line. To locate the point on this vertical line, I cut the distance from the top line to the x-axis in half. I'll sketch myself a horizontal line. Yes, maybe a little high. It's not perfect. Get the idea. Okay. And then I'm going to sketch another line halfway from that one to the x-axis. I'm going a little high again, so I'm going to correct that a little bit. And a third one. Then I'm going to start from this point. I'm going to go over to this line. And I'm going to go down 1, 2, 3 lines here. And I've got another point. Then I'm going to draw a vertical line halfway between the middle vertical line and the x-axis, the y-axis, I'm sorry. And now to get the point on this line, I have to go halfway from the lowest line that I've already drawn, the one I just drew the X through, to the x-axis. That'll be about here. Halfway from that to the x-axis. It's getting hard to squeeze that in. And then halfway from that one to the x-axis. That's going to be really hard to draw. And you're probably not even going to be able to see it, but you understand that it's almost right on top of the x-axis. Because every time we go halfway, our distance to the x-axis becomes half as great. And if you do that, 1, 2, 3, 4, 5, 6 times as I've done, well, you've cut this in half 6 times. That means that you have 1/64th the distance between the x-axis and the lowest line compared to the distance between the x-axis and the highest line. So this is 1/64th of this distance. That's really pretty small. Anyway, we can now do the same thing we did. Remember this point, we moved over to the next vertical line toward the x-axis, and then we moved down 3 horizontal lines. We're going to do the same. We've got 3 new horizontal lines here, so we can move over to the vertical line, down 1, 2, 3 horizontal lines. Well, that puts us really, really low. Now, we could actually lower than what I've drawn there, but we could continue doing this, okay? If we wanted to do another vertical line halfway between the y-axis and the nearest vertical line, then we'd have to divide this tiny distance, this distance that's 1/64th of the distance between the horizontal line and the, between the x-axis and the highest horizontal line. We'd have to divide that, subdivide it in half 3 times. And we would end up with 1/512th, that's right, 1/512th of this distance, the distance between the x-axis and the horizontal line, the top horizontal line. And that's so small that it would be well within the thickness of the chalk line here. So if we're over here, we haven't left the chalk line. And if we keep doing that, these distances grow smaller and smaller and smaller. And as we approach the y-axis, they're going to approach zero, so that where the x and y axis, or the x and y axes coincide, we get the point 0, 0, the point where the x and y axes cross. Then I can sketch a curve. Now that curve has to stay pretty much inside the x-axis for quite a ways until it finally comes up a little bit, goes through three points that I've sketched. Now this curve looks a whole lot like a parabola, like a y equals x squared. Well, if I want to do p equals 2, I can make a very similar construction, drawing my horizontal and vertical lines and putting a point where they meet. Then from the vertical line I just constructed, I go halfway to the y-axis. And then from the top vertical line, I go halfway down to the x-axis. And I go halfway down again. And I put a point. Okay, meaning that I move over 1 unit horizontally and down 2. Then I can do it again. Starting from the last horizontal line I drew, I go halfway to the x-axis and I get a line. Then I go halfway from there to the x-axis and I get a line. From the last vertical line, from the vertical line closest to the y-axis, I go halfway to the y-axis. So that now, starting from the last point that I drew, I can move one line closer to the y-axis and go down 2. Now I could actually go to another line here, halfway between the y-axis and the closest line, and I could subdivide twice more. And that would give me a point that's not quite in the thickness of the line for the x-axis. Now, we don't usually do that, but that process could continue. These points would continue to get 4 times closer to the x-axis every time I go twice as close to the y-axis. And the curve I get would look quite similar to the curve I got for p equals 3. Okay, now the p equals 2 function, be x squared, or could be any positive multiple of x squared. There's the shape of the graph. You see that the p equals 3 function, power 3 function, has more curvature than the power 2 function, which is half of a parabola. And we could draw the other half of the parabola. I'm probably not going to draw it very well. I didn't. It looks more like a cubic function on this side, but you understand that I've drawn the right half of the parabola. Depending on the scale of the x and y axes, this could be any multiple of x squared, any positive multiple. If you had a negative multiple of x squared, well, all your x values would be negative, and you'd have the same thing, but it would be down below the axis. The overall shape of your p equals 3 function is going to look something like this. We've seen why this function flattens out so much near the origin. So we make sure this one flattens out quite a bit toward the origin. If x is negative, its cube will be negative, which is why the graph goes down on this side. For the p equals 2 graph, the x squared graph, the square of a negative number is still positive. So that we're going to have a graph that basically looks like this. I'm going to attempt to draw this without putting a bunch of guide points in, but okay. As the power of the function increases, if we wanted to do the x to the 4th function, for example, we'd have to go over one line and down 1, 2, 3, 4 lines. And that would get out of hand real quickly. That causes the thing to flatten out a lot more quickly than the x cubed function, and much more quickly than the x squared function. If it was the x to the 4th function, the 4th power of a negative is positive. So the x to the 4th function is going to look much like a parabola, but it's going to be a lot flatter. So it's going to look something like this, by comparison. Much steeper as we get away from the y-axis, much less steep at the origin, and stays pretty flat. Now, I might have over-exaggerated. That might be closer to an x to the 6th function. I didn't construct it carefully. But if you follow the pattern that I used in constructing these two, you can see how to construct it. Similarly, a higher odd power. Again, when you have an odd power, if you take an odd power of a negative, you're going to get a negative. The graph is going to be quite similar to the cubing graph, but again, it's going to have to get a lot flatter at the origin. So if this is the x squared function, this graph here is the x squared function, and that graph is in blue. The x to the 4th function, or maybe x to the 6th, is going to look something like this orange graph. And if the x cubed function is the function that we just looked at, the x to the 5th or x to the 7th, again, question mark, is going to look like this. The higher the power, the steeper it is, and then the flatter it is. It starts out very steep, gets very flat. Okay, now, with that as a background, I want to talk about rational functions, but I'm going to do that in another video because it's very difficult to make this video ADA compliant because it's so graphical.